Folks, we've made it. Okay, it's the end of the semester, May the 3rd. Student study day. We've done a lot of things this semester. Okay, lots of up and down, some brand new topics, some easy, some challenging. Okay, but the theme that I have been trying to get across for all of you is these foundations. Okay, the idea is that we have to keep up with our foundations. Okay, the microphone's still picking up. That's good. We have to keep up on our foundation. That means our basic derivative integral pairs. We got to make sure we have those. Trig identities, values of trig functions, basic things like log of e to the 0, things like that. Because those are the building blocks to everything that we have done. Okay, everything has built up upon itself. Okay, a lot of you may not be taking a formal math class afterwards, but some of you may be using math in a different context. Okay, engineering students, raise your hand real quick. Okay, in particular, electrical engineering students, signals and systems, it's all integration by parts, Fourier transform, Laplace transform, solving ODEs and PDEs. You need integrals for that. Okay, mechanical engineering, physics, anybody? Taylor expansions, that's what you need. Okay, linear systems as well. Okay, biology, any bios majors in here? Pre-med even? Okay, differential equations. Okay, dynamical systems, disease modeling. Okay, all these have applications. Okay, doesn't necessarily mean you'll do the exact application of what you see here, but it will actually help you in your thinking. Okay, so right now on the notebook, I've compiled a big document that I wrote up last night, 35 or so questions. Okay, no, we're not going to do them all, but I want you guys to understand a few points here. All right, first off, these bullet points. Okay, focus on the how, not just the what. Okay, try to think logically. What is the next best move? Okay, any chess players in here by chance? Any chess players? No? Okay, yeah. Okay, well, you want to try to find that excellent move or that brilliant, that coveted brilliant move, the double exclamation mark. Okay. We ask ourselves, what theorem should I use? What result can I use? Why can I use it? Is it justified? How can I move logically from one step to the next? Are there multiple ways to solve the problem? Which one is probably easier? And does my work flow? Okay, can a buddy or my instructor follow my work with minimal stress? And I really stress this, okay? I don't like seeing the treasure map approach, where it's like a bunch of work on the page and it's like, here's the thing. First off, at least box your answers, okay? At least box your answers. But make sure that your work flows, left to right, top down. I'm going to try to model that in these notes here, okay? So we're going to go through a fair amount of exercises. I won't go through all of them. Okay, in particular, anything that involves some arithmetic, I trust you all know how to do the arithmetic, okay? So use your calculators and use them wisely, okay? I really stress doing these all by hand and then using the computer to check, not the other way around, okay? The computers are tools, okay? CASs are tools, Symbolab, right? Wolfram, okay? They're tools, but you don't just rely on them. You got to have some thinking with them, okay? We have a lot to cover. I'm going to try to make sure that you all are prepared, okay? So that being said, let's just go ahead and jump right into it. I want to go ahead and start with techniques of integration 1.1 here, okay? This is an assortment of integrals, but I've gone ahead and like grouped them into various classes, okay? So we have this guy here, x cubed sine of 2x dx, okay? We have a product of functions, okay? Now, of course, a lot of the integrands that we worked with had products, okay? But this is a particular kind of product that lends itself well to one technique. So I'm going to ask you guys to remember a thing. What was the very first brand new integration technique that we learned in this class? The very first brand new one. Integration by parts. IBP is supreme, okay? IBP is supreme, y'all, okay? I want to really make a point here. So this is one that lends itself well to IBP. Now, the question is why? Couple of ways. Anytime I see a polynomial against a sine, cosine, or an exponential, like this one here, that's a clue to use integration by parts. Polynomials against sines, cosines, and exponentials. Very well here. Okay. Now, let's go ahead and remind ourselves what the IBP formula is. So in this color here. IBP takes its form in this way. If I have the integral of u dv, okay, then I can write this as u times v minus the integral of v du. Now, of course, if we have a definite integral, okay, then of course we do the evaluation on the boundary for uv, okay? But what is this really? This is the product rule backwards. This is just the product rule backwards. Okay, I want to make a note of that here. This is just the product rule. So I want you guys to think about the product rule here. Now, there is a heuristic that we use in selecting U and DV. Okay, 5 letters, almost kind of sounds like a coffee drink. Okay, let's do this maybe in magenta. The heuristic, liate. The heuristic is liate. Logs, inverse functions, algebraic functions, trig functions, exponential functions. When we look at this from the top down, this is how we select our U. And from the bottom up, it's how we select our DV. Okay, we all remember this heuristic kind of, right? This kind of gives us a hierarchy, a rule of thumb. It's not set in stone, it just makes it a logical choice. Because the idea is you want to reduce your integral into something easier, okay? So let's just throw this out there. What do you guys think for this one I should select as my U and my DV? I'm open to ideas. What should I select as U and DV? Say that one more time. All right, U is equal x cubed. That's a good choice. So DV should be the rest. Okay, now let's remember a fundamental thing here. Do this in orange. When we go from U to DU, that's a derivative. That's just our power rule, right? And that we need the differential there, dx. And then when we go from dv to v, we integrate. So the antiderivative of sine 2x is, who remembers? Yes. Very good. Okay, negative 1/2 cosine 2x. Why? Antiderivative of sine is minus cosine. We divide by 2 because if we do a use of, where we think of the chain rule, everybody, the chain rule. And folks, all you got to do here is just follow your path. That's not the button I want to hit. uv minus the integral of v to u. Oh, that's a thing I didn't know you could do. Okay. So this integral, we can reduce this, okay? So the integral now becomes u times v, so minus 1/2 x cubed, cosine of 2x, minus the integral of v du. So we'll have a minus 3/2 x squared cosine of 2x dx. Now, yes, you can pull the minus sign out, turn that thing into a plus. But now look at what you got. Let me fix that, actually. You need to go ahead and do parts again. You would need to go ahead and do parts again. And when you do parts again, on a question where you have to do it multiple times, you make similar looking choices. So should I choose u to be cosine 2x in this case? No, because you'll get right back to where you started. You've made no progress. So you want, in this case, now you want to select u to be equal to x squared. Okay, similar looking choices, and then you keep going. Now, some of you may be thinking, but there's a faster way to do this, right? Well, yes, but I want you to also understand this classical formulation, because it helps you for things where, like, say, for example, like x log x. Okay, it doesn't really work out too well, that one. But for this one, for polynomials against sines and cosines and exponentials, you can use this following DI method. Okay, stand and deliver. Have you guys seen that movie, Stand and Deliver? Y'all should. It's a good movie. Okay. So the question is, do you have the ganas? Okay. So here's how we're going to do our DI method. Okay. I'm going to leave that there as an exercise, okay, for you to finish. But you'll see that you can get the same result by doing this table method. Okay. The D column is going to be all your U's, and your I column is your DV. Well, what do you think D means here in this case? What does D mean? Derivative. And what does I mean? Integral. So in the D column, you're going to differentiate. The I column, you're going to integrate. So we're going to go ahead and put our first thing in the D column there, which was x cubed. And in the I column, we'll have sine 2x. Now what we do is we differentiate down the D column until it vanishes, until that derivative is 0. 3x squared, 6x, 6, 0. Okay, we take derivatives until it vanishes. Then we're going to take the integral on the I column as many times as we differentiate it. So we want the same number of rows. Now, note here, because we're integrating sine of 2x, we're going to be dividing by 2 each times. So we get extra powers of 2, okay? Why? Use substitution, okay? That chain rule, okay? So when we think about that, okay, we have -1/2 cosine of 2x. Let's see, antiderivative of cosine is sine, so we have -1/4 sine 2x. Then I have 1/8 cosine 2x, 1/16 sine 2x. Looks like a lot, but this saves you a lot for a problem of this type. And now, as it said in the movie, tic-tac-toe. What we're going to do is we're going to make these shoelaces, okay? I'm going to take the first thing in the D column and join it to the second thing in the I column. Second thing in the D column to the third thing in the I column, and then you repeat. You do this shoelace pattern. Now you're going to go ahead and add some signs, some S-I-G-N-S, okay? They're going to alternate here. Plus, minus, plus, minus, plus. Now take a look. Each of these, each shoelace is a product. X cubed times -1/2 cosine 2x minus -3x squared times -1/4 sine 2x. Add all those things together, you have an integral. Okay, do we understand the DI method, how it can save your life here? Yes? We okay? Any questions? Okay, remember, polynomials against sines, cosines, and exponentials, DI method, fast. Okay, I'll leave this for you all to write out the actual antiderivative. All right, I want to go ahead and look at another one here. Simple one, arctan x. Arctan x. What kind of function is arctan x? Well, yeah, we're going to use integration by parts here, but what kind of function in the Liotte heuristic? Inverse trig I. So U is arctan x. That's our selection here. But what is dv? 1 dx, okay? Remember, there's an invisible 1 here. Now you just go ahead and fill in your table, right? uv minus the integral of v to u, okay? And take a look. Okay, so the integral of arctan x, by the way I write it right there in my handwriting, inverse tangent x, that's not tangent to the -1. I want to make sure everyone is clear on that. That is not the same as the reciprocal of the tangent function. Are we clear on that? Okay, please do not make this mistake. That is not the reciprocal of the tangent function, but it is the inverse of the tangent function, hence the inverse tangent. Okay? So by doing parts, we have x arctan x minus the integral of x over 1 plus x squared dx. There are two ways to attack that integral at the very end. One is a little more natural, and one we learned 2 sections after we learned integration by parts. Who wants to tell me the easy way of doing this? Anybody? Yes. A u sub. And what would you make your variable change? Very good. Okay, so one way of attacking this, let's do this in orange, okay? One way of attacking, since we already used u, I'm going to use z, okay? So I can make the substitution z equals 1 plus x squared. So dz is 2x dx. That's one way I can attack this. That's the natural way of doing this. Okay, so good on you for that. But there is one other way that you can attack this. Anybody have any ideas how? Yes. Say that one again. A trig sub, but what trig sub? What trig sub would I use here? I see a sum of squares. I think tangent sub. 1 plus tangent squared, folks, is secant squared. And so I can also do this move here, which is the brilliance. This is the brilliant move. I can set, say, x equals sine t. Sorry, not sine t. Sorry. x equals tangent t. So dx is secant squared t dt. Okay, derivative of tangent to secant squared. You don't have to use, like, I know you're probably used to using the variable name theta in this case, but you can use whatever variable name you want. I just don't want to write theta because it's going to get messy the more I write it. So does everyone see where that one came from? Okay, again, because 1 plus tangent squared is secant squared, we might need that for a question. Okay, either way, no matter how you go about it, you will get the following results. X arctan x minus 1/2 log of absolute 1 plus x squared plus a constant. No matter which way you go about it, that's the antiderivative that you get, and you're done. And this is such a powerful technique, everyone. Integration by parts is the granddaddy technique, as I call it. Okay, very useful in understanding differential equations, especially in mechanical and civil engineering, the finite element method. Okay. I want to do one last example of integration by parts. But before I move on, any questions? Are there any questions? Don't be shy. Okay. I'm actually going to go ahead and move on to number 4. Let's take a look at this integral. Okay. Let's take a look. Cosine of square root of x. Y'all remember seeing this in your homework set, right? Something like this. I can guarantee you it was in there. It doesn't look like an integration by parts question, right? But I can tell you it is after you do a variable change. Wouldn't it be nice if that square root wasn't there? Right? Like, what's the antiderivative of cosine? Let's just ask that question. What's the antiderivative of cosine? Sine, right? So if that square root wasn't there, it would just be sine x plus c. Okay, we win. But we're integrating the cosine of the square root. What function undoes square roots? What is the inverse function of square roots? Squaring, yes. So the trick here is to do what I call a priming substitution. We're going to go ahead and prime this. We'll say t equals, actually, let me make sure I'm doing this right. I'm going to prime this with x equals t squared, okay? Because if I put in, instead of square root of x, I have square root of t squared. What's the square root of t squared? Just t, right? That's why I want that. So x equals t squared. So what is dx? 2t dt. There you go. 2t dt. We've done a priming substitution to turn this hard-looking problem into a more manageable looking problem. Because, folks, look at what happens here. When I go ahead and make that substitution, cosine of square root of x. Well, x is t squared. And what do we say the square root of t squared was? T. So we have a cosine t there. And dx is what's now? 2t dt. 2t dt. And folks, what technique do I use here? Integration by parts. IBP is supreme here. We have a product of functions. So look, product of functions, okay? Polynomial, 2t, against cosine. Lends it well to parts. So I just want to leave that there for y'all, okay? This is IBP once again. Okay, you can go ahead and use your DI method here. So 2t cosine. Okay, take derivatives until it vanishes. Take integrals in the other column. So sine t. And then minus cosine of t. And then we're going to do, I don't want to use yellow. That's bad. Okay, plus minus plus. We do these shoelaces. Okay, let's do purple here. Tick, tack, toe. And so take a look at what comes out of here. When you join all the shoelaces here, we get minus 2t sine t. And then minus 2 times minus cosine t. So minus times minus is plus. What am I missing? Say that again. Plus c. But am I really done? No. The original problem was an x, so we got to go back into x, right? So we got to change those t's back into x's. That's where we go back here, okay? If x is equal to t squared, that means t is equal to the square root of x. We go ahead and back substitute, okay? We get minus 2 square root of x, sine of square root of x, plus 2 cosine square root of x, plus a constant, and folks, you are DONE done. Yes?
For a lot of the integration by parts for everything, or does it need to be saturated?
So that's a good question. So can we use the DI method whenever we want? Well, DI can help you organize any IBP, but it's the most powerful when you have a polynomial against a sine, a cosine, or an exponential. Okay, so let me actually make that a remark here. So we can use this for polynomial. P is a polynomial here. Polynomial against exponential. Polynomial against sine. Or polynomial against cosine. Okay, that's what I mean by this against that, okay? You can use this table to help you organize information, but the key thing is here is maybe something doesn't vanish entirely. For example, the one I skipped, x to the 4th log x, the choice of u, there will be u equals log x. We'll take derivatives of log x over and over again, as we might need to do for a Taylor expansion. It doesn't vanish. But the polynomials will. Okay, so it's very nice to have that classical formulation of integration by parts in your mind. Yes? Say that one more time. Ah, yes. So the negative 2t, I really hope this still picks up on. Actually, wait, can I just like. Yeah, maybe. Okay. So how do we get the negative 2t? Okay, so oh, actually, you know what? Yeah, I did make a mistake. Yes, you're right. That should be a plus, right? Plus 2t times sine t. Thank you. Thank you. Yeah, that should be a plus. Yes, thank you. All right, any other questions? Let's go on to the next one, 1.5. All right, so I have cosine cubed of 4x. So now we're leaving the realm of IBP, and we got to get into the T word that a lot of people hate. And it's not tensor, because that's my T word. I don't like tensors. For you physicists, you'll like tensors anyway. Okay, the T word here is trig. Okay, these are families of trig integrals. Okay, whenever we do a trig substitution, we're going to reduce to something just like this. Or maybe with secants and tangents. So how do we handle them? Okay, there are lots of heuristics at play here. All right. Now take a look here. We have cosine cubed of 4x. Okay, I have a linear function there in my as the argument of my cosine as my angle. But what I'm going to do to like save myself some trouble, I want to go ahead and just do a priming substitution, so it looks a little simpler here. Okay, so let's go ahead and prime this with t equals 4x. So dt is equal to 4 dx, okay? I want you all to be comfortable with using different variable names, okay? Yes, it's called u substitution, but that doesn't mean like u is the only letter you're allowed to substitute for, okay? X, Y, Z, okay? U, V, W, okay? T, theta, whatever you want, okay? So when we solve for the differential, we'll get 1/4 dt equals dx just by dividing by 4, playing for the match, okay? Basic u substitution, okay? So our new integral that we're going to look at here, which is just going to form the basis for the thing that we're going to look at here, is cosine cubed of t dt here. Okay, the 1/4 we'll just ignore for the end, okay? Because integration is linear, I'm allowed to do that. All right, so how do we handle this? I don't have a formula for cosine cubed, okay? We don't know complex numbers because that's the way to cheese it, okay? But trig functions, like onions and ogres, have layers. Y'all are probably too young to remember Shrek, okay? That's fine. What I'm going to do is do the following. The rule for sines and cosines is I want to peel away one of them. I have an odd number of cosines. I have 3 cosines. So I'm going to peel it away. And so what we're going to get here is 1 cosine times 2 cosines. Okay. But why is this helpful? Because I want to be able to force a variable change. We're trying to play the most forcing moves here, okay? Do I have another way of writing cosine square? I have 2 ways to, well, I have probably like 5 ways to write it, but which way is going to be the most useful here? Anybody? 1 minus sine squared is the winning move. Very good. So we're going to go ahead and write, so this in green. Okay, we're going to go ahead and write that as 1 minus sine squared. This is going to be the powerful move here. We have cosine of t times 1 minus sine square of t dt. Okay, all this is the same. And do you see the variable change that we have to make? What's the variable change? Anybody? Well, first off, give me your favorite letter of the alphabet. Say that again. U? Okay, fine. We'll use U. That's not what I want to do. What should I set U equal to here? What should be my variable change? Sine of t, yes? And that makes du what? Say that again. It's a positive cosine t, not a negative. Okay, remember which direction you're trying to go in, okay? That does the job for us. Because take a look here. Okay, this thing here in the blue, that's right there. And so what do we have? 1/4. The integral of 1 minus u squared du. That's just the power rule because you have the power to rule, okay? It's just a polynomial. We know how to handle that. 1/4 times all this stuff, u minus 1/3 u squared. U cubed, sorry. Plus the constants. And now we just unravel, right? U is now sine t. And t was 4x. So in fact, what I'm going to do here is just be lazy. There you go. Any questions on that procedure? Yes. Yes. That's a very good question. So the question is, do we choose the trig function that's inside the parentheses? Yeah, mostly. But remember the heuristic for tricks, just general change of variables, right? You want to have a function and its derivative appear in there, right? We have sine, and the derivative of sine is cosine. Now, you could argue, well, the derivative of cosine is minus sine. Yeah, but I have a sine square in there. Okay. So you want to choose it that's like inside the parentheses, quote unquote. Okay, the one that has like more stuff going on with it, because it'll reduce it to some polynomial type thing. That's a very good question. Yes. Yeah. So if I remember, yeah. So if you have an odd number of cosines or an odd number of sines, you want to work with the odd ones, and then you need to like try to force like a 1 minus sine square or 1 minus cosine square to some power. And now if it's like, if it's like x minus y squared, don't say it's x squared minus y squared because no, you have to cross term, right? Just use the F word to expand it, not that F word. Okay. That's been the running joke of the semester, guys. So yeah, you got to be a little careful with those. Okay. But yeah, you want to expand, peel away with the odd ones. Now, if you have even ones, which, can I turn the page? Okay. If you have even ones like this one, okay, then you have to use the hint here. Sometimes called the power reduction identity, sometimes called the half angle identity, or if you have a certain instructor, he calls it the golden identity. Okay. Power reduction, half angle, golden identity. Now, which identity am I referring to? If you have the formula sheet in front of you, it is there. And so I'm going to go ahead and give you the one that we'll need here. Okay. So the hint here says to use the following. We're going to need sine square of y as 1/2 of 1 minus cosine 2y. That's what the hint says. Half the value, double the angle. I'll say that again. Half the value, double the angle. Note that the angle is now twice of what it was before. We have before sine square y. Now I'm taking the cosine of twice y. And I take half this value. Okay. Many ways to rewrite sine squared and cosine squared if you remember from pre-calc. Okay. Some of them are more useful than others. This one's the useful one. So let's just go ahead and think about this right away. We're going to go ahead and use this hint. So the integral of sine squared 3x dx is equal to the integral of 1/2 of 1 minus cosine. So I got half the value. Now I double the angle. What's twice my angle here? 6x. Now it's an easy integral. Straightforward. Multiply through. Okay, you have a constant there, so it becomes a linear function because of the power rule. We're integrating cosine. We know how to handle that. So let's go ahead and handle this here. 1/2 times antiderivative of 1, x. Antiderivative of cosine. It's sine, right? So we'll have a minus sign here. But because we have a 6x there, I need to account for the chain rule there. Divide by 6. Very nicely done. Okay, I want to stress there is like a little hack that you can do with u substitution. Okay, if your innermost function is a linear type function, or should be more precise, say affine function, but who cares? If it looks like a line, right? Mx plus b, same antiderivative, but then you got to divide with the slope at the end. That's what we did here. We good so far? No questions on that one? That one was really straightforward. I want to move on to secants and tangents next. Okay. So let's go ahead and skip down to 8. How are we doing on time? It is 3:37. Wow. Okay. Oof. All right. Secant to the 4th times tangent squared. Now we have secants and tangents. Pop quiz. What is the derivative of tangent? Secant squared. What is the derivative of secant? You're fired. The derivative of tangent is secant times tangent. Okay. Now, how can you reconstruct those? Well, tangent is sine over cosine, and we use the Q word, the quotient rule, to get that derivative. Secant is 1 over the cosine. We use the chain rule there, or the quotient rule if you want to. Same thing. But for secants and tangents, you want to be able to work in pairs. You want a secant-tangent pair or a pair of tangents together. Now let's think about this. I have 4 secants and 2 tangents, okay? Let's get, the one identity that we're going to need to use here in some fashion here. 1 plus tangent squared t is equal to secant squared t. We're probably going to need something like this, okay? Now the question is, how do I work with this? The move here is I'm going to go ahead and peel away 2 secants from the 4. I'm going to peel away 2 secants from the 4. So I have secant squared times secant squared times tangent squared. All right. Now take a look at the identity that I just wrote down. Can I use that in some way? Remember, for these kinds of things, I want to force a variable change. What can I do here? I'm open to options. Substitute 1 plus tangent squared for secant squared. That's the winning move. We're going to go ahead and I'm going to highlight that in the same color. I can take one of those secant squares and just replace it with the 1 plus tangent square. That's exactly what we're going to do. So I'll write secant square here. 1 plus tangent square. Another tangent square. Now I'm at the point where I want to make a variable change. Okay, choose your favorite letter of the alphabet other than U. R. I mean, yeah, sure, we can integrate in polar coordinates if we want to. Yeah, so let's do R, okay? I'm going to do R equals something. What am I going to set R equal to? Say that one more time. Tangent x, okay? R is equal to tangent x, so dr is secant square x dx. And now you see it here, okay? Check it out, okay? I got tangent squares there, and secant squared x dx is like our du earmuffs there. Or in this case, our dr earmuffs here, okay? All right. So we do our variable changes here. Let's see, we have 1 plus r squared times r squared dr. And at this point, it should be straightforward, yeah? Multiply through. You get a polynomial now. Use the power rule because you have the power to rule. And now you just unravel. And so I'll leave that there. Any questions on that while I figure out how to plug this thing in so that we still have a recording? Yeah, I'll let you guys digest that for a second. Okay. Okay. All right, now I want to move on to like what I think is going to be really fun stuff, okay? 1.10. By using an appropriate trigonometric substitution, evaluate this integral, x times square root x squared plus 16 dx. The final answer should not include expressions such as sine of arctan x or arc cosine of sine x. The strongest shape, folks, the triangle. Trust in the triangle. We'll get there. Now, if you didn't want to use a trig substitution, what else could you use here? Any ideas? Section 1.5, folks. A u sub. Set u equals to x squared plus 16. So du is 2x dx. X dx is 1/2 du. Probably the more straightforward way, but I want us to understand how to do this with the trig subs, okay? We have a sum of squares. Okay, and think back to that identity we just had before. 1 plus tangent squared equals secant squared. Doesn't that look like what we had in our integram? Something squared plus something squared, right? That motivates the identity to use. A lot of people have asked me, Sean, how do I figure out which substitution to use? Think about the Pythagorean identities because those motivate the substitution that you want to do. So let's look here. We have x squared plus 16, okay? I want to make the variable change. X equals 4 tangent t. Okay? Dx is 4 secant squared t dt. Now, why does this work? Well, let's plug in and see what happens, okay? Well, x squared plus 16 If I plug in x for what it is now, it's the function of t, 4 tan t squared plus 16. We got the square of a product, so it's going to be the product of squares. 4 squared is 16. Tangent squared t plus 16. I use the other f word, factor, to pull the 16 out. And folks, what do I have? 16 times tangent squared t plus 1. But what's 1 plus tangent squared? It's secant squared. That's why this is so powerful. 16 secant squared t. And now take a look what happens when I go ahead and take square roots of all this nonsense. Square roots are multiplicative. The square root of 16 is 4. The square root of secant squared is, no, it's absolute secant t. We're going to ignore that. It's secant t. We're in excellent shape here because now everything collapses nicely. So let's look at what our integral is now. We have the integral, that's not a good looking integral sign. The integral of x square root of x squared plus 16 dx. All right, now let's think. X is 4 tan t. And we already figured out that the stuff inside the square roots is 4 secant t. Salud. All right, folks. 4 fours gives me how many? 4 fours. 4 times 4. 16, right? I'm going to pull the 16 out. I have secant t, tangent t, dt, and what's that antiderivative? El secante, yeah? Secant. Okay, picante secante, right? Plus a constant. But are we done? The original problem was an x. So how do I go back into x? The triangle, folks. We're going back to pre-calc. We're going back to classical high school geometry, okay? So here's how we draw the triangle. We take, I'm going to do this in yellow. That's not the color. This guy here, okay, x equals 4 tangent t, that's going to help us build that triangle, okay? So let's go ahead and draw this off here. We have x equals 4 tangent t. I want to get the trig function by itself. So what do I do? Say it one more time. No, I want to get the trigonometric function by itself. Divide by 4, okay? X over 4 equals tangent t. Why am I doing it like this? 9 letters. SOHCAHTOA, okay? Because I'm going to draw a right triangle, and I want to write this as a ratio of parts. So tangent is going to be what over what? What part of the triangle over what part of the triangle? Say that one more time. Opposite over adjacent, okay? So my angle here is t, okay? Draw your triangle and mark your angle. Mark your angle. It helps immensely. It helps immensely to mark your angle. Opposite over adjacent, so we have x over 4. Can I get the missing side? How can I get the missing side? Pythagoras, right? We're going to use Pythagoras. X squared plus 4 squared. Take the square roots. And by the way, before I forget, I'm going to lean in close for this. Square root of x squared plus 16, is that the same as x plus 4? No. Square roots are not additive. Square roots are not additive, folks. Very fundamental mistake that a lot of people will still make at this stage. So please be very careful with that. Okay? If we had that, we wouldn't have Pythagoras in the first place. I want the secant of t. I don't like working with secants, cosecants, and cotangents. So I'm going to try to put this in terms of sines, cosines, and tangents. But secant is a reciprocal of which function? Say that again. Cosine. What is the cosine of t here? There you go. Right? So I need cosine of t, which is, I'm going to put this in a different color, actually. Cosine of t is 4 over square root x squared plus 16. And so secant of t is just that reciprocal. The square root of the thingy divided by 4. And after we do some stuff, because 16 divided by 4 is 4, we have 4 times square root of x squared plus 16 plus a constant. So you see how these trig substitutions lend themselves to getting it back to a trigonometric integral of some type. This one was easy because we had secant times tangent. But it could easily be powers of secants and tangents, or powers of sines and cosines, or, God forbid, cosecants and cotangents. Same thing, just with a minus sign. Okay. Any questions on this process? Yes. Say that one more time. Yes. So when we take our original substitution here, I'll put it back in yellow. We just take the differential on both sides, okay? Take the yes, okay. So x is 4 tangent t, and then dx, let me do this in a different color here. It's not the prettiest color. I just want some variety here. So dx is 4 secant squared t dt. Okay. So dx here is now 4 secant squared t dt. Okay, derivative of tangent to secant squared. And then we just follow the steps there. Okay. These are good questions, folks. Yes.
Is x is 4 tangent t, I see that, and then dx is 4 secant squared by itself, and then we also have the 1 in the square root. So would that make it 16 secant squared t? Like from the dx, and then also
Yes, but then we take the square root at the end. So hopefully this, let me actually do it on this side here. So, and I'm going to project it low so it still picks up. Oh, it still kind of is. Okay. So here, square root of x squared plus 16, we plug in for x, which is 4 tangent t. We do some stuff, plug in. And then in the end, when we take square roots here, we get the square root of 16 secant squared t. The square root of 16 is 4 square root of secant squared is secant. And now we just lump those together. So this guy here, I really am running out of colors. Let's see here. This thing here corresponds to folks, it just goes to show you that even the masters make mistakes. All right, let's try to salvage this. Okay, for those watching the recording back, you can probably fast forward through this. Yeah, let's kind of reconstruct this. So x is 4 tangent t. That's in yellow. Then dx is 4 secant t dt. And then the square root would give me another 4 secant. Okay, yeah, there we go. Okay. I guess I can kind of reconstruct this a little bit. But the solution notwithstanding, this just kind of, okay, that's not good. The solution kind of gives you an idea like how to reason with this. Just make sure that you keep track of everything. Okay. Does everyone see where I did go wrong though? Yes. Okay. Just make sure it's. But a lot of these substitutions, you might have to like keep track of these things. I'm kind of gonna leave this in the recording. Okay, but like yeah, just make sure you put it into correct parts in the correct places. So x is 4 tangent t. The square root stuff is 4 secant t, and then we have an extra 4 secant t. 4 secant squared t from the differential. So we're going to end up basically integrating tangent times secant cubed, which I think is actually oh, wow. That is actually literally the last problem. That's problem 9 right there. So it actually reduces to problem 9. Okay. Thank you. Thank you for that. Okay. Yeah, just make sure that like you keep everything in line. Okay. Okay, we're good. All right. Let's try to do one more where I don't botch this. Let's see. Let's do 11. Let's do 11. Let's just set up 11 and then we can move on to other topics because I want to make sure that we also get to some of the applications and then of course the power series, the real analysis stuff. Okay. Number 11 here. 1 over x squared times the square root of 4 minus x squared. Which substitution do you think? Any ideas on which substitution to use? Well, yeah. Which one? It is indeed sine, right? And why is this? Why is it sine? Because we want to think about one. That's not the one. We're thinking 1 minus sine square equals cosine square. That's exactly what we're thinking. 1 minus sine square is cosine square. Number squared minus variable squared. Okay. So, choose another letter of the alphabet. Choose another letter of the alphabet. That's the square root of -1. We can't do that. Yeah, right. Whatever. Let's make C a continuous variable here. So we're going to go ahead and make the following substitutions. I might regret this decision. So we're going to have C. Oh, no, sorry. We're going to have X equals 2 sine C. I already am regretting this decision. Okay. Now, why is it 2? Because the square root of 4 is 2. Okay. Dx is what? What is dx? 2 cosine C. My favorite kind of shoes. DCs, yo. Okay. I'm actually a Vans guy, so not a sponsor. Okay. Now we're gonna go ahead and plug stuff in. Okay, so dx there. Well, let's actually write everything down so I don't mess up again for the benefit of everyone. Okay. Or I may just scrap this recording entirely. So we have this integral. Whoops. And now I'm just going to go ahead and replace stuff, okay? So dx is 2 cosine of C dc divided by x squared, that's 4 sine square C, and the square root of 4 minus x squared, so it's going to be 4 minus 4 sine square C. Okay. I can pull the 4 out of the square root, and it comes out as a 2. So we have 4 sine square C. Pull the 4 out as a 2, and then what's left in the square root is 1 minus sine squared, which is cosine square. Square root of cosine square is cosine. Now take a look. My 2's drop. My cosines drop as well. Okay, and now I'm just left integrating 1/4 times the integral of 1 over the sine square of C. But what's 1 over sine square? Or rather 1 over sine square. 1 over sine of C. Cosecants. The integrals of secant square and cosecant square are basically the same. So I'll spoil that for you. You basically do end up getting a minus 1/4 cotangent C plus a big C. Okay. And now you just unravel the substitution. Okay. I'll leave that there. Okay. All right. I want to show like 2 quick examples of partial fractions, but I'm not going to do the partial fraction like the integral net results. I just want to show the algebra steps, and that would be okay. So any questions? Let's move to 13. Okay. All right, so I have the integrand. Now, could I do a trick up here? Yeah, tangent, but we're not. Partial fractions, PFD, okay? Don't write that. All right. Now, the theorem says that, like, basically, if I have a bottom-heavy rational function which means one where the degree of the denominator is bigger than that of the numerator, we can break it up into a somewhat simpler fractions. So let's take a look at what we have here. We'll do some black. We have 1 over x times x squared plus 1. I have a linear factor in x and an irreducible quadratic in x squared plus 1. Every sum of squares is an irreducible quadratic. Now, if you are comfortable with complex numbers, you can break that in as x plus I, x minus I, and do everything else there. But I don't expect you to. Even I don't do that if I'm not asked to. Okay? So the linear factor gets its own thing. This is going to be something over x. And then for the irreducible quadratic, at worst, that numerator is going to be linear. Bx plus c over x squared plus 1. Okay? At worst, the irreducible quadratic is linear, has a linear numerator. Now, if we were able to factor that quadratic, that gives us two linear factors. So like if I did the complex number thing, x plus I times x minus I, I'll have like b over x plus I plus c over x minus I, but we're not going to do that. Okay? So this is what happens. You have a sum of squares here, irreducible quadratic, x squared plus number. All right, now what we're going to do is clear fractions. I want to clear fractions by multiplying by the common denominator. We're just undoing the fraction addition. That's all we're doing. So we're going to fraction bust here. On the left, I'm going to have a 1. Let me actually write out what I'm doing here. I'm going to take this and multiply both sides by x times x squared plus 1. So on the left, I have a 1 left over. And on the right, I'm going to have an a times x squared plus 1, then plus bx plus c times x. Does everybody see where that came from? Yes? Does anybody need me to explain that step I just did? I'll be happy to. Yes. Okay, yeah, so let's go ahead with that, okay? So the step here is as follows. I have this thing here, and I want to go ahead and clear the fractions. I want to multiply by common denominator, okay? So the common denominator here is just x times x squared plus 1. Because think about it. If you went right to left, how do we add and subtract fractions? We get a common denominator, right? So the common denominator I just multiplied through. And so I'm just undoing that. So I'll have x times x squared plus 1 times 1 over the thingy. Those cancel. And on the right-hand side, let's take a look at what happens. A over x times x squared plus 1. Well, the x's vanish. So I have a times the sum of squares. And then likewise for the bx plus c thing, that thing over x squared plus 1 times the thingy, the x squared plus 1s vanish. So I just have the x left over. Good questions, y'all. I like these. Okay. Now the problem is, how do I handle this? Two ways. A system of linear equations, if you want to, by equating coefficients, or the cover-up method. We're going to go ahead and get the easy one out of the way here. The cover-up method just basically says choose clever values of x, okay, to get you to eliminate some of the parameters and solve for one unknown. In this case, I'm going to go ahead and choose x equals 0. Why? Because if I choose x equals 0, the last term vanishes. 0 times junk is 0, so that last term is gone. And so on the left, I just still have the constant 1. And on the right, I'll have a times 0 squared plus 1. That's just a. I got a for free right there. Boom. So I can go ahead and erase here and put in the value of a there. Now, let's pop quiz. Integral of 1 over x. Integral of 1 over x. Anybody? Natural log of what? No. Absolute x. That's a nice subtlety there. You have to have the absolute value there unless the thing inside the absolute value is positive. All right. Now, the problem is here, I've run out of clever x values to use, so we're just going to choose like the next best one. So maybe like 1 and minus 1, and that just gives me a system of two equations. So I'll write them out here. If x is equal to 1, okay, I'll get the equation 1 equals, okay, now that I already have A, I can actually already use it. A is 1, so I can use that freely. 1 times 1 squared plus 1, 2, plus x is equal to 1, I get B plus C. Okay, B plus C times 1. Now, if x is equal to -1, I'll do a similar thing. On the left, we still have a 1. On the right, okay, -1 squared is a plus 1. 1 plus 1 is 2. A is 2. A is 1, excuse me. Now let's take a look at what happens here. When x is -1, okay, we'll get a -1 times b times -1 plus c. Okay, we just substitute x equals -1. Okay. Now let's go ahead and tidy that up a little bit, okay? I'll get 2 minus, I'm kind of regretting this already, negative b plus c. We have 2 plus b minus c. I have 2 equations and 2 unknowns. So namely, I need to solve, let me go ahead and shove stuff over here on both of those. So we're looking at this one and this one here, okay? For the first one, if I move the 2 over, I get b plus c has to equal -1. On the second, I have b minus c equals -1. Something feels fishy here. I think this should have been like a positive one here somewhere. Let's think about this, okay? I plug in x equals -1 into here. I get negative b plus c times the -1. Which is what I have here. Multiply it through, get a plus and then a minus. Actually, I think it should still be able to work out. Now, if any of you are familiar with systems of linear equations from like college algebra, okay, or if you know some basic linear algebra, you can like do substitution, you can do elimination. I can add those 2 equations. B plus b is 2b, or not to be, that is a question. But what is c plus a negative c? 0. So those vanish. -1 plus a -1 is a -2. And that gives us that b is equal to -1. Okay, so we're going to go ahead and fix the screen here. Okay, so b is equal to -1, so we'll go ahead and put that in there. And now, how do I solve for c? Well, I plug in the value of b into one of those 2 equations and get the value of c, and it turns out that c is equal to 0. Now, doesn't that thing look easier to integrate now? One of them is a log, but actually both of them are logs. Both of them are logs. I leave that as an exercise. That's the partial fraction idea, okay? Does anybody have any questions on the recipe and the method? All right. I at least wanted to show you like that one partial fraction example. This one, for the case of repeated linear factors, just count up, okay? Go back and watch the video. In fact, that kind of recipe is actually on your formula sheet already. Okay, understand the recipe in the formula sheet. I'm only going to talk about improper integrals very quickly, but because we have one extra step. Let's just take a look at this one, for example. If I didn't have the limits of integration there, if I didn't go from 0 to infinity, what method of integration would you use to handle this? Not a U sub. It's parts, because it's a polynomial against an exponential. Well, what's the only extra thing that we got to do now? Plug in limits of integration and take a limit. That's the only extra thing for improper integrals. Nothing new. You know how to do antiderivatives. You know how to do definite integrals. Improper integrals are just one step further. You're just now doing a definite integral where one of those limits just shoots off to infinity or some other thing. You're just taking a limit. That's it. So a very abridged version of this, I'll tackle this with the DI method. Choose D equal U equals X. Then we have the rest is e to the minus 3x. And you see how very quickly the DI method kills it all, right? Tic-tac-toe, right? But what's the extra step? You're passing to a limit. That upper limit is going to vary and go out to infinity. So we go ahead and toss in our antiderivative here. So minus 1/3 x to the x times e to the negative 3x minus 1/9 e to the minus 3x. We do the same exact thing as we did before, but now we got to ask ourselves a question. What happens as t goes to infinity? So we plug in okay, we plug in our stuff, then we get a number. Turns out that that number in the end is going to be let's see. If I plug in 0, get a 0 for the first term. E to the 0 is 1, so we got a 1/9. But now we're only worried about the limit for the left-hand term. Does that make sense? And this is where you think about some of your basic calc 1 stuff, okay? E to the negative 3t, think about that as 1/3 to the t. As t gets large, e to the t gets large, but you divide 1 by a very, very big number, you get a very, very small number. You can make it as small as you want. That goes to 0. And it actually turns out in a similar vein, the second term goes to 0. Okay, for the sake of time, I'm going to leave you guys to show that, okay? Because I still want to get to some quick applications in the power series. The only new thing that you're doing with improper integrals is just taking a limit, and that's it. That's the only thing that you're doing. Improper integrals just add that extra step. No questions on that? Two point two. For now, I'm only concerned about writing the integral that represents the integrals for these things, okay? We're not going to compute the integral, although that's an easy exercise, just arithmetic, okay? But I want you to know how to construct these things. So I have the region of the plane bounded by these two curves, okay? We have y equals x squared and y equals another thing. Which of those two curves is y equals x squared, red or blue? Red. So blue is the other. Now, area between curves. There are 3 words. 3 little words. What were those 3 little words? Top minus bottom, you should be saying that in your sleep. Say that on the car ride home. Okay, say that to your dog. Okay, shout it from the rooftops. Top minus bottom is all you need for area between curves. What do you mean by that? We take a representative strip here. That little rectangle has height that represents the distance between those two curves, top minus bottom. Then we add up all those little strips. But what do we have to do, really, when we set up this integral? We got to find the limits of integration. Oh, the picture tells me that it's from 0 to 2. Okay, what if you don't have the actual grid? Set the two things equal to each other. X squared equals 6x minus 2x squared. Okay? Shove stuff over. Okay, we have x squared minus 6x equals 0. That's not right. Wait a minute. That should be a 3. There we go. Add 2x squared to both sides, okay? Now factor, okay, GCF. I have 3x times x squared minus, 3x times x minus 2. So we have x equals 0, x equals 2, and that certainly agrees with my picture here. Now I'm going to go ahead and try to do this in the same color. So the area, the integral that represents the area is the integral from 0 to 2. I want to fix this 2 here. The integral from 0 to 2 of the top function minus the bottom function. Easy task. Easy task. 3 little words. Top minus bottom. But now what if I want a volume? Rotate this region around the line x equals 0. What integral represents this volume? Before you attack any of these problems that talk about an area between curves or a volume, draw the picture. Draw the picture. Without the picture, you get nothing. So many times, a lot of people have asked me, like in office hours, right in the math gym, and it's like, they have a question like this, and they stare at it, which, is a natural response. But then I say, okay, what should you do first? Sometimes they say, oh yeah, draw the picture. Like, yeah, go ahead and draw the picture. A picture tells 1,000 words, but sometimes it can also tell 1,000 lines. Okay? So x equals 0. The line x equals 0 is the y-axis. We're going to go ahead and draw the arrow that represents that turn. And now what I'm going to do is I'm going to imagine. Okay, I'm going to imagine that I turn this around. Discs or shells? Discs or shells? Shells. It's more of a visual gag. This is a rectangle. Length times width. Okay, but if I glue the two edges together, I haven't changed the area of the shape. We're working the same topology here, okay? But the surface area of the cylinder, I've just wrapped the rectangle. 2 pi RH. That's on your formula sheets as well. But what are the R and the H? H here is a shell height, and guess what? We already know what that shell height is. Top minus bottom. Okay, we're going to use shells here. Also, I want you to remember this. Shells are parallel. Shells are parallel. Okay, we slice parallel to the axis of rotation. That means we're talking about shells, okay? So we want 2 pi times the integral from 0 to 2 of a radius times a height. Now, the good news is we already have the height, and that's that integral there in the integrand, okay? So this thing, which I'm going to color in yellow, I hope it doesn't mess it up too much. This thing here is my shell height. Well, what about my shell radius? The shell radius is the distance from one representative strip to the axis of rotation. So this little strip here is at some position. Let's call it X. That's not good. Okay, that strip is at some position. Let's call it X. And I'm going around X equals 0. What is the distance? The other 3 little words. Sorry, I got to do it this way. Right minus left. Shells uses both the top minus bottom and right minus left principles, everyone. So the radius here is just X. So the integral that represents this thing, X times the thing above. 6x squared, 6x minus x squared minus x squared. That's the idea. Any questions on the shell construction? Any questions on the shell construction? Shells are parallel. Shells are parallel, okay? 2.4 real quick, okay? I think area should be easy, right? Area between curves is super easy. I trust we can do that. Let's look at 2.4 here. I got the OG log, log, okay, but it's actually natural log, okay? Keep it all natural, okay? Y equals 2 log x, y equals 0, x equals 1, and x equals EA sports. It's in the game. So that green line there is x equals E. I'm going to go ahead and color in the region that we're talking about. Trace it out, right? 2 log x, y equals 0, x equals 1, and x equals E. That's the region I'm talking about. I want to rotate this around x equals -1. Draw it in. And now let's think here. Discs or shells? Discs or shells? Shells, because shells are parallel. Look at how I sliced in the light blue. And that's parallel to the axis of rotation. So this one we're using shells. Okay, the shell height should be easy. It's just log x. But what about the shell radius? The distance from a strip to the axis of rotation, right minus left. Okay, think about the radius here. It's some x minus, we're going around x equals -1. And everything is there in your favor. Do we have that clear? Yes? Are we okay with that construction? Okay. Now, for discs, well, I spoiled it already. Part B says to go around y equals 2. Let's do that in red here. If I rotate around that line, I'm using discs. But that's a washer. Yeah, I know. Same thing. Outside squared minus inside squared. You got to think about what is the outside radius and what's the inside radius. Okay. We have this distance here and this distance here. Should do that in a different color. And how do we think about that? Top minus bottom again. Outside radius squared, 2 minus 0. Okay. Minus inside radius squared. That inside radius is 2 minus 2 log x squared. Does everybody see that? How that's the inside radius? Yes? Okay, so very quickly, the integral for that, be pi times the integral from 1 to e, outside radius squared, so 2 squared, minus inside radius squared, which we said was, oh, so there we go. 2 minus 2 log x. I think this one you might have to do integration by parts on, but that's how you construct it. Okay. Let's look at 2.7 real quick. I want to do a very quick physical applications one. Okay, really trying my best to get through a lot of examples. Okay, for you all. Okay. How many of you have taken physics 1? All right. If I'm talking about ropes and springs, what's the only law that matters? Peter Pan and Captain Hook. Hooke's law. The idea for Hooke's law is that the force required to displace a spring is proportional to its displacement. That's our basic idea. Now, we can think of ropes as springs, okay? In a sense, where the spring constant is really that weight per linear foot or linear distance, okay? So let's take a look at this question. We have a cable that weighs 2 pounds per foot, and it's used to lift 800 pounds of coal down from the bottom of a mine shaft 500 feet deep. How much work is done in doing this? Draw the picture. Cable. Bunch of coal. Okay, Santa would be happy to give these to naughty boys and girls, right? Okay. The coal has fixed weights. And the mine shaft is 500 feet deep. Now, I know that this is 2 pounds per foot. That's a tensile strength. Can I get the total weight of the cable? Think about the units, right? Multiply the weight per foot of the cable by the length of the cable. Okay, so I'm going to denote this as force of cable at some position X, okay? So the cable initially weighs 1,000 pounds. So you also know that this is people that are afraid of metric because we're talking about coal and we're using imperial units. Okay. The cable weighs 1,000 pounds, 2 times 500. But think about it. As you pull that cable up, you're pulling up less and less at every stage, right? So we should be subtracting. If I pull up 1 foot of cable, I pulled up 2 pounds. 2 feet of cable, I pulled up 2 pounds. So if I pull up X feet of cable, I'm pulling up X pounds. That is the weight of the cable at any, say, position X. Now, as we said, the coal has fixed weight, right? How do we get the total work done? The total energy required to lift this entire system up? Total work is an integral. We're going to integrate from 0 to 500 of the sum of these two force functions, okay? These two systems are coupled together, and so we just add everything. So we have 1,000 plus 800, that's 1,800, minus 2x dx, easiest integral in the world. Easiest integral in the world. Okay, many questions have their own variants. Please watch the physical applications videos, okay, for more examples of this. All right. I'm going to give you guys a quick real analysis 1 treatments. Okay, sequences and series of functions. Okay, I take it that we're kind of comfortable with sequences and series of real numbers. We just tested on that. Okay, please go ahead and watch back that material if you haven't already. But everything from this next chapter, chapter 6, relies on everything that you know from chapter 5. Same tricks too. Let's take a look at this one, 3-1. I have a function f, 1 over 1 plus 2x squared, and I want to expand this as a power series near 0. What is the radius and interval of convergence? The trick for a lot of these questions where it just says expand as a power series, that kind of thing almost looks geometric, right? It almost looks like the sum of some geometric series. Here's our trick here. As one of the instructors that I had put it when I had it for complex analysis, the main reference series that you're going to use is 1 over 1 minus q. That definitely is a geometric thing, right? Just replace it with r if you're comfortable with it. This is just a sum from n equals 0 to infinity of q to the n. Now, the thing is, what is q in this context? I want to get 1 minus a thingy, okay? The trick here you want to write that denominator as 1 minus a negative 2x squared. That's the trick. That is the trick. You want to write it like that because it identifies the thing that's in the blue. And now q is just this thing here. And so we expand. Okay, we use the result from before. Minus 2x squared to the, that's terrible. Minus 2x squared to the n. I can shuffle some things around. I'll have x to the 2n, because power to a power makes it a superpower. And then I have negative 2 to the n. That's my power series. That's my power series. Now, the question of radius and interval of convergence. What thing do I usually have to do to get radius and interval of convergence? Five letters, starts with R. Ratio test. We usually do the ratio test. But here's the good news. You already know that this is a geometric series. Forget the ratio test. Because when does a geometric series converge? The common ratio has to be what? Less than 1? There's more to that. Less than 1 in absolute value. Okay. So this thing converges when the absolute value of negative 2x squared is less than 1. Okay. So we solve this inequality. Okay, I'll spare a bit of the details. Okay, we solve this inequality, we'll have absolute x squared is less than 1/2. Okay. And this also implies that because we have something squared, it's always positive. Okay. So I know for a fact that this thing is greater than or equal to 0. Now, how do I undo squares? Say that one more time. Let's take the square root. Very good. So we'll have that absolute x is less than 1 over square root 2, and is bigger than or equal to 0. That's your interval of convergence at the very least. We know it's going to converge at 0. Okay, if you plug in 0, it makes sense, okay, into the expansion. But how do I check the other endpoints? How do I know that it converges on the other boundary points? We got to plug it in. So we check. Check this by plugging into series. Okay, whenever you want to look for the interval of convergence, okay, you have to check the endpoints as well. There's a theorem that says that if a power series converges, it at least converges on an open set. We don't know about the boundary. We have to check the boundary. Okay. Questions on this one? Just giving you enough to kind of give the full solution here. Okay. Speaking of interval of convergence, I just want to show another example. Okay, 3.3. Okay, where you actually have to use the ratio test. Okay. On what interval does this thing converge? First ratio test. Okay. So we do the ratio test here. So we want the limits as n goes to infinity of something. Here, we're going to identify our ANs here as -1 to the n squared, x to the n over 2 to the n. Now we do our usual ratio testing, right? Look at the next term, the n plus first term, divide that by the nth term. Now, notice here I'll have a -1 to the n and a -1 to the n plus 1. If I take the absolute value of that, that's just going to be 1. So are we okay if I omit the -1? Are we okay if I omit that? Okay. So we're going to look at n plus 1 squared. That's oh, wow. Guys, I'm very tired. My handwriting has suffered. N plus 1 squared, x to the n plus 1 over 2 to the n plus 1. And now we're going to multiply by the reciprocal of the original stuff. 2 to the n squared, x to the n. Start canceling. Exponent rules. This is what this is about. Exponent rules. Okay, when we look at all the stuff that will cancel nicely, we'll have an x. Actually, we'll have an x over 2. And then we're going to have an n plus 1 square over n squared. This limit only depends on x. Can I pull it depends on n. Can I pull the x out? You bet, but I got to pull it out in absolute value. And in fact, I can also pull out the 2 as well. And just by using some properties from calculus 1, that limit on the inside is 1. And so we have that this is absolute x over 2. Here. and I want this to be less than 1. Now we have to solve that inequality. We get our interval of convergence. To get the radius of convergence, we take the width of the interval, divide it by 2 to get the radius. Think about diameter versus radius. And then we have to check the boundary. Hint, for one of these, you're going to have to use the alternating series test. That's an alternating series criteria. Yes. Yes. So if you have absolute x squared, you know that that for sure is going to be greater than anything squared. Anything to an even power is going to be greater than or equal to 0. Yes. So let's go ahead and finish this out here. So we have absolute x is less than 2. And then the general rule for absolute value inequalities is that absolute x less than c. I'll just use k here. Absolute x less than k. That means negative k is less than x is less than k. It's an inside. It's an and. Okay, college algebra, right? We just solved that inequality. And in fact, that gives you the interval already right there, minus 2 to 2. Interval a radius convergence of 2, but we're guaranteed convergence on this open set, but we got to check the boundary. You have to plug in x equals 2, x equals negative 2. So you have to check the boundary. All right. I want to look at 3-7. Okay, I want to show you a couple of Taylor. Well, I would rather want to show you like one Taylor series example because then this helps you for all. Okay. I want to expand this function g. Okay, e to the minus x squared. Statistics people, this is going to be your favorite function, the Gaussian. Actually, the physicists as well. Okay, e to the minus x squared. I want to expand that near 0, and I give you the hints. First, expand e to the x. Then, in that expansion, replace x with negative x squared. This is powerful. So let's just do the expansion for e to the x, okay? So let's try to expand e to the x. Remember the Taylor expansion. Okay? The Taylor expansion is the only Taylor that you need. It's the only one that matters in this world. See, that's a joke on a certain pop star. Okay? Hey, I'm in my graduating era, okay? I can say what I want, okay? I'm in my graduating era. Okay? The Taylor expansion works like this. We're going to take the nth derivative of our function, evaluate it at a center point, scale it by a factorial, and then I'm going to get powers of x minus a. So what do I need? I need derivatives. I need these factorials, and I need the powers. So we're going to do the first thing. We're going to take derivatives of this thing. What's the derivative of e to the x? All right. What's the derivative of e to the x? What's the derivative of e to the x? So every derivative is e to the x. Now, the thing is, what's the derivative of e to the x at 0? What do? We plug in 0 into all of these. In fact, since I already have the general pattern here, I just plug it into the derivative. So the nth derivative of f at x is just e to the 0, but what's e to the 0? 1. I have part of my Taylor coefficients. Now, I got to scale it by n factorial. So I take that nth derivative there, divide both sides of that relationship by n factorial. And folks, you just built my favorite Taylor expansion. So e to the x can be written in this infinite sum. 1 over n factorial times x to the n. But did I want to expand e to the x? No, I want to expand e to the negative x squared. And so the trick here is what I'm going to do. I'm going to replace x here. with negative x squared. And folks, the only thing that changes here is that. Now we alternate, okay, because I have negative 1 times x squared. So negative 1 to the n times x squared to the n, but power to a power makes it a superpower. We multiply. X to the 2n. Divide by n factorial. Best expansion ever. And fun fact, this expansion converges everywhere. The radius of convergence is infinity. I'll leave it as an exercise to show that the ratio test gives you a limit of 0 independent of x. So this converges uniformly everywhere. Any questions on that? So what is the framework for any Taylor series question? Start by taking derivatives of your function. Try to look for a pattern. Okay, here it just eats the x straight up. But for those ones where it's like 1 over x or 2 over x, you'll get like maybe some factorials already built in there, some alternating signs maybe. Find your pattern. Scale it by n factorial. Evaluate your derivatives at that center point. And then you get those Taylor coefficients. It's about the framework. Try to organize all the information that you have. And here, you need derivatives. So start off by taking derivatives and finding that pattern. Then figuring out a pattern in what the values of derivatives are. Scale. Plug stuff in. It may seem tedious, but folks, this is such a powerful tool. Differential equations, integration techniques. They all come from Taylor expansions. All right. Looks like we are basically out of time. I want to thank everyone for coming out today this late on a study day. And folks, it has been my pleasure to have you all as part of my last classes as a TA in my last semester here at UTSA. Thank you.